All right, here's some more information about stoichiometry. If you're still a little bit confused about our previous lesson, then I would recommend that you go to the bottom of this module and watch the first couple. There's a video that says optional that will give you a couple more examples about how to do stoichiometry, just the basic stuff. There's a couple at the end that we haven't discussed yet in that video, but the first two or three, I believe, are just more examples of basic stoichiometry type problems. So now what we're going to do is we're going to step it up just a little bit. We're still going to be doing some stoichiometry, but what we're going to be doing is we're going to make it a little bit more challenging from what we did the other day. So these are additional stoichiometry problems, and we'll just start. We're going to combine what we've learned about stoichiometry with empirical and molecular formulas, things that you've also learned about. Remember that the molecular formula is what we call the real formula. That's like glucose is C6H12O6. That's the molecular formula. The empirical formula, remember, is just the ratio of one to the other. So this is the molecular formula. The empirical formula for glucose is just CH2O. So in our previous lesson, we learned about using the balanced equation to convert from the moles of one substance to the moles of another. That's what we call stoichiometry. And in our previous unit, we learned about how you can go from percent by mass to the empirical formula of a compound. Remember that rhyme that we learned? Percent to mass, mass to moles, divide by small times till whole. That's what this is referring to here. Now what we're going to do is we're going to use stoichiometry. We're also going to use that percent to mass rhyme to combine the two together. So a lot of times what you'll be given when you're given a stoichiometry type problem is you'll be given the name of a compound that you're unfamiliar with. Or it might even say an unknown compound. For example, here they're talking about propane gas. If you happen to know the formula of propane, this is a real easy problem. But in most cases, they're going to give you a compound, or I'm going to give you a compound that you don't automatically already know the name or the formula of that compound. So, but what you can do is you can use the information about the products to determine the empirical formula of this unknown or this unfamiliar compound. So let's take a look here. It says 8.410 grams of propane gas combusts in excess oxygen gas to form 25.23 grams of carbon dioxide and 13.76 grams of water. Now, I think this is the first time we've seen this word excess. You're going to start seeing that a little bit more often when dealing with stoichiometry. And the reason that we use that word excess just means the word extra. And we're going to talk about this actually in our next lesson. But when you think about a chemical reaction, when you run out of one of the reactants, the reaction stops. And so the reason that we say 8.410 grams of propane gas combusts in excess oxygen, it's basically all that we're telling you is that there's extra oxygen left over, that the oxygen is not going to run out, that this reaction is going to stop when this amount of propane is all used up. Okay, so we've got 8.40 grams of propane, which we don't know the formula of. It's going to combust in oxygen, and it's going to make some carbon dioxide and some water. So our job here is to figure out, oops, I guess is this the same one here? No. So our job here is to figure out what is, and I actually forgot to put the question here. The question is, what is the empirical formula of propane? So based on that information, what is the empirical formula of propane? So let's look here. Propane, we don't know what it is. We do know that it's going to form some carbon dioxide and it's going to form some water. So it's some compound plus oxygen going to make CO2 and H2O. Now, we don't know what's in this compound, but we know we've only got three choices. It can have carbon in it, it can have oxygen in it, and it can have hydrogen in it. It doesn't necessarily have to have all three of them, but it has to have at least one or more of those compounds. Just like we learned about the law of conservation of mass or the law of conservation of matter, you can't have some nitrogen over here and no nitrogen over here on this side. Okay? If your products only have carbon, oxygen, and hydrogen, then your reactants can also only just have carbon, hydrogen, and oxygen. Okay. So obviously here we can't use a balanced equation because we don't know what one of our reactants is. So we can start by using this formula right here, but it doesn't really help us much because we don't have a balanced equation. Now here's the key to understanding this problem. There's some oxygen here. Obviously we've got oxygen here and oxygen here. Clearly this reactant right here has to have some carbon in it and has to have some hydrogen in it. It might also have some oxygen, we don't know at this point, but it definitely has to have some carbon, it has to have some hydrogen, because again, the only reactant we know of is oxygen. So the other reactant has to have the other products in it, so it has to have carbon and hydrogen in it. Now the question we want to ask ourselves is if we look at this carbon on the product side, again this one, we want to think, where did all of that carbon come from? Well, it had to have come from this compound right here. So if we can use stoichiometry to determine how much carbon we have on our product side, however much carbon we have here, according to the law of conservation of mass, that's how much carbon we had over here as well. So we know that we have 25.23 grams of carbon dioxide. So let's use that information, 25.23 grams of CO2. And what we want to do is we want to use stoichiometry to get how many grams of carbon are in that 25.23 grams of CO2. So it's pretty similar to what we did the other day. If we've got grams of CO2, we're going to convert to moles. There are 44 grams in 1 mole of CO2. Now, yesterday what we did, or in our last section, what we did is now we would go from moles of CO2 down here to moles of whatever they were asking us about. However, in this case, we're not converting to another substance. What we want to do is we want to go from moles of CO2 to just moles of carbon atoms. And we can do that. Think about a mole of CO2. What that means is we have 6.02 times 10 to the 23rd CO2 molecules. If we had that many molecules, how many carbon atoms would we also have? We know that for every one CO2 molecule, there's one carbon atom. So if we have 1 mole of CO2, then we also have 1 mole of carbon. So that is what we're going to use for our mole ratio. Instead of using the coefficients for the balanced equation, we're going to use the number of atoms in the actual formula. So 1 mole of CO2 has 1 mole of carbon in it. Now, let's say that we were actually trying to figure out oxygen. It would look really similar. We would still have 1 mole of CO2 on the bottom, but on the top, we would put 2 moles instead of 1 mole. Right here, instead of 1 mole, we would have 2 moles of oxygen, because for every 1 CO2 molecule, there's actually 2, you can see it right here, 2 oxygen atoms. So we're using the formula to go from the whole molecule all the way down to the individual atoms. And now we can say, all right, 1 mole of carbon has a mass of 12 grams. So we're going to go 25.23 divided by 44, all the ones we don't need to do anything with, times 12. So I get an answer of 6.88 grams of carbon. Okay? So again, what that means, coming back to our balanced equation, if there are 6.88 grams of carbon on the product side, How many grams of carbon have to be on the reactant side? Over here, the same number. So we know that whatever this thing is here, whatever this formula for propane is, it has 6.88 grams of carbon in it. Now, we need to do the same thing, but now we need to figure out how much hydrogen we have. So it tells us it makes 13.76 grams of water. So let's do basically the same thing. 13.76 grams of water. Using my periodic table, there are 18 grams in 1 mole of water. And now we can say 1 mole of water has how many moles of hydrogen? Look at our formula. Every molecule of water has 2 hydrogen atoms. So a mole of water is going to have 2 moles of hydrogen. And then our last step, 1 mole of hydrogen has a mass of 1 gram. Okay, so now we can go 13.76 divided by 18 times 2 equals I'm going to round that to 1.53 grams of hydrogen. So now we're to the point where we can try to figure out what is actually in propane. Is it just carbon and hydrogen, or is there some oxygen in there as well? Because when we come back to our balanced equation, this oxygen that's in the carbon dioxide and this oxygen in the water, it could have all come from this oxygen right here, but there could actually be some oxygen in that first formula. So let's figure out how we might know that. If we have 6.88 grams of carbon and 1.53 grams of hydrogen, and we add those two together, we're going to end up with 8.41 grams. 6.88 plus our 1.53. Add those up and you'll see that it equals 8.41 grams. So what does that tell you? It tells you that propane only has carbon and hydrogen in it. If the number was lower, let's say it was only like, 7.25 grams, then you've got, 1.16 grams of something left over, and so that's where your oxygen would come in as well. So then we could figure out, okay, how much oxygen is actually in it? Oh, it's, 8.41 minus 7.25. And that would tell you how much oxygen is in this propane molecule. All right, so we know that propane only has carbon and hydrogen in it, and these are the masses that we have. So let's take this information, 6.88 grams of carbon. So 6.88 grams of carbon and 1.53 grams of hydrogen, and let's get the formula. Let's get the empirical formula of propane. So if now we need to remember our rhyme. Our rhyme says percent to mass. We've already got our masses. And then percent to mass, mass to moles. So let's change these grams to moles. Obviously, this one's still going to be 1.53 grams, or excuse me, not grams, moles of hydrogen. 6.88 divided by 12 equals 0.573 moles of carbon. So percent to mass, mass to moles, divide by small. Our smallest number is our 0.573. So we're going to divide both numbers by that. So that gives us 1 carbon. And when we divide 1.53 by 0.573, we get 2.67 hydrogens. And hopefully we realize, okay, that's similar to 2/3. So we have to multiply the whole thing by 3. And so our formula comes out to be C3H8. And that is our empirical formula for propane. And in this case, it actually is also the molecular formula. The actual formula for propane is C3H8. H8. And that's it. So now when I say that's it, that's obviously kind of joking, because there's actually quite a bit you have to do there. There's some stoichiometry in there. There's the using that rhyme. So this is going to take a little bit of practice for you to do. Okay, let's look at one more and see. And this might be a point where you stop the video and you try to do it yourself. And if you get stuck, then come back. Okay, so again, 1.97 grams of an unknown compound, so we're just going to call it X, completely combusts. That means it reacts with oxygen. And again, it's going to make CO2 and H2O. So we've got 1.97 grams of this unknown compound. We've got 3.94 grams of CO2 and 1.61 grams of water. So first thing we want to do is we want to figure out the empirical formula of this unknown compound. We want to know what's the formula of that thing. So we're going to take our 3.94 grams of CO2 and we want to figure out how much of that is actually just carbon. So again, 44 grams in 1 mole of CO2. 1 mole of CO2 contains 1 mole of carbon atoms, and 1 mole of carbon has a mass of 12 grams. So 3.94 divided by 44 times 12 equals 1.07 grams of carbon. And then for water, the same thing, 1.61 grams of H2O. There are 18 grams in 1 mole of water. From the formula for water, we know that 1 mole of water contains 2 moles of hydrogen atoms, and a mole of hydrogen atoms has a mass of 1 gram. So now we're going to take 1.61 divided by 18, multiply by 2, and we get 0.179 grams of hydrogen atoms in our compound. So if we've got 1.07 grams of carbon and 0.179 grams of hydrogen, let's look and see if there's anything left there. So we've got 1.97 all total. So we have 1.07 grams of carbon plus 0.179 of hydrogen, and that only adds up to let's say 1.25 grams all total. So we know that there has to be something else in here. So if we take 1.97 and subtract 1.25, we get 0.72 grams. So there's 0.72 grams of something else in this compound. Well, again, look at our products. We have carbon, we have hydrogen, and we have oxygen. Those are your only 3 choices, are those 3 elements, because there's nothing else on our product side. So we know that 0.72 grams has to be grams of oxygen. So this formula here, whatever this unknown compound is, has to have some oxygen in it. So we're going to take 1.07 grams of carbon, 1.07 grams of carbon. We're going to take 0.179 grams of hydrogen, 0.179 grams of hydrogen, and our oxygen, 0.72 grams of oxygen, and now we're going to try to figure out the empirical formula based on that information. Okay, so percent to mass, mass to moles, 12 grams in 1 mole of carbon, 1 gram in 1 mole of hydrogen, and 16 grams in 1 mole of oxygen. So 1.07 divided by 12 equals 0.0892 moles of carbon. This one's going to be the same number, 0.179 moles of hydrogen, And then for oxygen, 0.72 divided by 16 equals 0.045 moles of oxygen. Okay, so percent to mass, mass to moles, divide by small. It looks like the 0.045 is our smallest, so we're going to divide everything by that. And so 0.0892 divided by 0.045 is 1.98, so we can round that to 2. So that's 2 carbons. 0.179 divided by 0.045 is equal to 3.98. We can round that to 4 hydrogens. And then oxygen is obviously still a 1. This divided by this equals 1. So now our last step, percent to mass, mass to moles, divide by small, times till whole, we don't need to do because we've already got all whole numbers. So our equation is C2H4O. And again, in this case, that is our empirical formula. Now, our last step is, let's come back here to the question. The question says the molecular formula has a molar mass of 88 grams per mole. What is the molecular formula of this compound? So remember now is here where we have to figure out the mass of this thing. So carbon weighs 12, there's 2 of them, that's 24. 24 plus 4 is 28. 28 plus 16, this one has a mass of 44 grams per mole. The molecular formula has a mass of 88. So we have to think 44 times what number equals 88? Obviously that is 2. So we take this whole equation right here and we multiply everything by 2. So our molecular formula ends up being, let's get rid of some of this here. If we multiply that whole thing by 2, we're going to end up with C4H8O2. That is our molecular formula for this. Okay, and that is 2 examples of using stoichiometry to convert from the mass of a compound to the mass of an individual atom within that compound or within that molecule. And really that's the key to understanding this process, is taking the moles of the whole molecule. For example, if you have 1 mole of C6H12O6, you could say that has 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. And it's being able to make a mole ratio out of those things to convert from the whole molecule to just the individual atoms.